Good morning, good afternoon, good evening. My name is Xianjun Jiao. I'm from China. I'm now working in ID Lab, Ghent University IMEC, Belgium. Let's talk about our recent work from our quite small SDR research group, Software Defined Radio Research Group. Recently, we have released a free and open source Wi-Fi implementation on an FPGA or SoC, because in that chip there is FPGA and ARM processor. Let's start from a sentence I like very much. That is, what I cannot create, I do not understand. That's from the Nobel Prize winner Richard Feynman. Another explanation about that sentence is that when you learn some equations, you think you understand it, but only after you can derive the equation from scratch on an empty paper, then you can say you understand it. That's a way to learn, I would say. So, what about creating a Wi-Fi chip? So, I believe almost every people use Wi-Fi chip every day on their cell phone, on their laptop, on their computer. But do you know how Wi-Fi chip works in the real world? We did some research, that means search again on the internet. We find out that the Linux operating system has created a quite good, clear and clean Wi-Fi framework to support many Wi-Fi chips. So when we say build Wi-Fi chip, actually we are saying build this tiny thing. And meanwhile, after you build the chip, you also need to release a Wi-Fi driver. Then after that, all the rest work, you just reuse Linux. Linux have defined all the APIs, MAC 802.11 operations, and your Wi-Fi driver only need to implement those APIs. Then all the rest Linux will handle. For instance, create Wi-Fi AP, set your laptop, connect to another Wi-Fi AP, set your Wi-Fi device in ad hoc mode, match mode, etc. Linux will process all the rest. You only release two things, Wi-Fi chip and Wi-Fi driver. The driver has to be aligned to the Linux predefined APIs. That's how real-world Wi-Fi chip work. So, after we are clear on that, then we consider how to verify our Wi-Fi chip design before we do the tape out, because tape out costs lots of money. No one will design the chip tape out directly. So always the first step, you try to verify your chip design with some programmable platform like the software defined radio method, right? On the left, there's a host PC, and you use the R frontend together with the host PC. That's the very popular software defined radio architecture. On the right, you can choose FPGA board and connect the FPGA board with a front-end board. In that case, the FPGA can access IQ sample or the signal from antenna very fast. In the traditional software-defined radio way, on the left, the computer RF latency is larger than 100 microsecond. But on the right, the latency between FPGA and antenna is less than 5 microsecond. That means the FPGA platform is more feasible for our Wi-Fi chip verification. Because as you know, in the Wi-Fi standard, there is a time called SIFS, short interframe space defined. In 2.4 GHz is 10 microsecond, 5 GHz is 16 microsecond. The meaning of SIFS is that when you receive a packet, for instance, RTS packet or data packet, you have to send out acknowledgement in 10 microsecond or 60 microsecond. Meanwhile, if you are not sending, receiving, you still need to monitor the channel on the order of microsecond. update your network allocate vector, etc. Anyhow, a Wi-Fi chip is required to operate precisely on order of microsecond, not like the LTE system. The feedback is scheduled after 4 milliseconds in the HARQ procedure. So after this analysis, seems like we can start our work. Use the FPGA platform to design our Wi-Fi chip. Okay, let's start. Now, today, here comes the open source Wi-Fi baseband chip design under AGPL v3 license. You don't need to remember our website, the GitHub address. You just search openwifi. You will find it because currently the project becomes quite popular. We follow the basic framework defined by Linux. As I said before, we have released the FPGA design, which is in Verilog, high-level synthesis, and some block diagram. We also released our driver in Linux to encapsulate our design towards Linux predefined APIs. We also released a user space small tool to set our Wi-Fi card, read status from our Wi-Fi card, and access some unique features in our Wi-Fi card. A unique thing of our design is that the Wi-Fi chip here is FPGA and the computer, actually they are in the same chip because we use the Xilinx Zinc FPGA where there are both FPGA and ARM processor. So our Wi-Fi chip is sit together with the Linux, with the FPGA in the same physical chip. Here are the main features. We support 11A-GN protocol. Currently it works in 20 MHz bandwidth, cover almost all the frequency below 6 GHz. We have tested ad hoc mode, station mode, AP mode, monitor mode. You can enable more mode because, as I said before, the mode actually is implemented in Linux. And yes, as I said before, we have to operate the signal, the packet, receive, transmit in order of microsecond precisely according to the standard, Wi-Fi standard. So the CSMA-ZA, the low MAC layer is in FPGA. We achieve 10 microsecond shifts. And you can also configure many parameters, such as the duration field of the RTS, CTS, or CTS to self. In that way, you can manipulate the channel occupation according to your requirement, according to your service. You can also configure many other timing related parameters, contention window, slot time, etc. And we also support quite simple time slicing mechanism, where we can assign the packet targeting specific MAC address to occupy specific portion of the channel time. And it's a software-defined radio platform, so you can change the bandwidth easily to 2 MHz or 10 MHz for IoT application or for vehicle-to-vehicle application. As you know, the 11AH and 11P standard. On the roadmap, we plan to do new standard like Wi-Fi 6 or Wi-Fi 7. So the ping speed is significantly lower than the commercial Wi-Fi chip or commercial Wi-Fi architecture. Our ping speed can as low as 400 microseconds. But the commercial Wi-Fi chip, they always connect to CPU via a quite complicated channel like the PCIe, like the USB, right? So our benefit is that our design is a system on chip. So you have low latency feature there. Regarding the throughput, we have tested our openwifi design, the FPGA board, against the commercial Wi-Fi device. We can communicate with commercial Wi-Fi chip or Wi-Fi device, and the throughput achieve the same level as commercial one. So currently we have extended the design to several FPGA platforms, from low-end Z board, several hundred euros, to the high-end ZCU102 board, several thousand euros. A reminder is that we never build hardware. We run our design on this off-the-shelf FPGA development board. You can just download the design from GitHub, and if you already have the board, you run the design immediately, and you can have a software-defined radio Wi-Fi AP or Wi-Fi client. If you don't have these boards, you can buy them anywhere because they are off-the-shelf board, not from us. The usage of the board actually is quite straightforward, and just like Raspberry Pi. You download our design, flash the design to a SD card, plug in SD card, power on the board. Then SSH log in to the board via Ethernet. Bring up the software-defined radio Wi-Fi interface. The name is SDR0. After that, you can run host ABD or WPA supplicant, any standard Linux Wi-Fi application. To start, use the software-defined radio Wi-Fi card just like a normal Wi-Fi chip. So, talk is cheap. Show me the code. That's another sentence I like very much. But don't worry, I won't show you code line after line. Just give you a brief introduction of all the building blocks. All these materials, you can find more detailed information in GitHub. We already write quite comprehensive documentation there. You can also find this figure there. For instance, from top to down, top there is Linux predefined IEEE 802.11 operations API. That's the green part is Linux, not us. Our implementation starts from the purple one. We have built Wi-Fi driver, SDR driver. There are many component drivers. Some driver is for register, read, and set. Some driver is in charge of the DMA, because in IPGA we have to use DMA to handle Wi-Fi packet between the IPGA and Linux. And in IPGA, the design, all the necessary building blocks of a Wi-Fi chip are there. You can find all the source code of this building block, such as the openwifi TX, that's the Wi-Fi transmitter. We have built the Verilog-based Wi-Fi transmitter according to the Wi-Fi standard. You can find all the detail here. That's the physical layer part. Receive packet, generate IQ sample. Like the openwifi RX, this is the Wi-Fi receiver. All the physical layer processing steps needed are there. You can see the source code. The synchronization, channel estimation, channel equalization, convolutional decoder, CRC checksum, etc. Many details. You can check, you can modify if you have the capability. The XPU in Central is the low CSMA low MAC. It's quite complicated state machine design. It implements the low MAC procedure defined in the standard. We have read standard carefully and implement necessary functionalities there. RX interface, TX interface handle the IQ sample to and from ADC, DAC, and also handle the packet interface to and from the ARM processor. There are also the queue management, because Linux needs Wi-Fi driver, Wi-Fi chip to have some queues. There are lots of Linux predefined functionality. Linux community also explain them very well. You can find many materials there. Anyhow, I cannot explain the whole design in minutes, but it will be a very valuable time, I believe, if you spend on our source code. So, how to use our design? Actually, you define. For instance, in our main, the very straightforward usage is the education. Because we have created the Wi-Fi chip, that means we understand Wi-Fi chip now. We can then teach it to anyone who want to acquire this knowledge. And for a researcher, definitely you can test many your new ideas based on our design. If you have some great idea to improve the Wi-Fi performance regarding the RF front-end, if you build a better RF, you can interface your RF to the IPGA, to our IPGA design. Then you test your RF in the real Wi-Fi network. If you have new signal processing algorithm for the physical layer, like channel estimation or CSI information-based sensing or radar application, you just implement your new idea in our physical layer module or replace some module and test your idea in the real world. You have new Mac design, you have a more efficient Linux driver, or you want to optimize the network across all the layers, or you want to do the security research, because I know many hackers, they definitely need to modify Wi-Fi chip to do the research, but as you know the commercial Wi-Fi chip is not possible to modify. But start from our design, you decide. If you have some special use case like low latency, time synchronization, or long-range communication to your drone, to the car, feel free to test our platform and integrate your new idea for your special application. And if you want to implement the new standard or even unreleased standard like Wi-Fi 7, some feature from Wi-Fi 7, you can start from our design to try those new features, to see how those new feature performs in the real world. If you have enough funding, sure, you can tape out a real Wi-Fi chip. So the real Wi-Fi chip will be much cheaper than the IPGA board. So I believe you will have much more customers than our current IPGA design. So these slides we cannot avoid. We are not from scratch. There are already some related works. We already put links in this page, and you can also check out those designs in the paper. We have pointed out the very important difference between our design and those previous designs. I believe our design currently is the only active design, and you can access for free and for open source code. So thank you very much. Any questions?